Hello everyone. So here we shall start the part 2 of this video on moving charges and magnetism. So here we shall solve some more previous year KCET questions on this chapter. Um, so in the previous part we had solved till the question number 37, and so here we shall start from the question number 37 onwards. So any doubts if you have, or in any steps of the solutions if you are unable to understand, then please write us in the comments section. And if in any other chapter of physics, if you feel more difficulty, then please mention the name of that chapter in the comment section. Also, some important homework questions on every chapter will be uploaded in the Sapience Education application. So please install our Sapience Education application, whose link has been provided in the description. So in question number 38, it is told, what is the value of the shunt resistance required to convert a galvanometer? One galvanometer is there, its resistance is Rg, is 100 ohm, into an ammeter of range 1 ampere. So its range should be 1 ampere. So one shunt resistance should be connected in parallel with the galvanometer, so that it is converted to an ammeter of range 1 ampere. Full scale deflection of the galvanometer is 5 milliampere. So it means that when through this 5 milliampere current is flowing, then through the main branch 1 ampere current should flow. Since the range of the ammeter is 1 ampere. So the current Ig, the current through the galvanometer is 5 milliampere. So Ig is 5 into 10 power minus 3 ampere. So Ig should be equal to S by Rg plus S into the main current I. So current I is 1 ampere. So this will be 5 into 10 power minus 3 is equal to S by 100 plus S into 1. So this will be 100 into this. So this will be 0.5 plus 0.005 S. So that is equal to S. So this will be S into 1 minus 0.005. So that is 0.995. That is equal to 0.5. So S will be equal to 9.95 by 5 ohm. Oh, sorry. S is 5 by 9.95 ohm. So option B is the correct answer. In question number 39, it is told a circular coil is there, a circular coil of radius 10 centimeter, and it has got 100 turns, so N is equal to 100, and it carries a current of 1 ampere. Then what is the magnetic moment of the coil? The magnetic moment of the coil, that will be equal to Ni into A. The number of turns is 100 and the current I is 1 ampere, and the area of cross section, that is pi r square, that will be equal to pi. So r is 0.1 meter. So r square, that is equal to 0.1 square. So this much ampere meter square. So this will be 100 into pi into 1 by 100 ampere meter square. So this is pi ampere meter square, which is 3.142 ampere meter square. So option A is the correct answer. Then in question number 40, it is told that a charged particle experiences magnetic force in the presence of magnetic field. One charged particle is there, its charge is q. It experiences a magnetic force in the presence of a magnetic field, which is B. Which of the following statement is correct? Uh, so the charged particle experiences magnetic force in the presence of magnetic field. Which of the following statement is correct? The particle is stationary. So the magnetic force is given as q v cross b. So it means that it should have a velocity. It should have a velocity which is at some angle to the magnetic field. Then only it will be able to experience some magnetic force. The particle is moving and magnetic field is perpendicular to the velocity. The particle is stationary. The particle is moving and magnetic field is parallel to the velocity. Okay. So it means that so some component of velocity should be there, which is so some component of velocity should be there, which is perpendicular to the magnetic field. Then only some magnetic force will act. So it means that option B is the correct answer. The particle is moving and magnetic field is perpendicular to the velocity. Then in question number 41, it is told if a velocity has both perpendicular and parallel components while moving through a magnetic field, what is the path followed by a charged particle? Okay. If a velocity has both perpendicular and parallel components while moving through a magnetic field, so it means that the velocity is at some angle to the magnetic field. So it has one component which is parallel to the magnetic field, which is v cos theta, and one component which is perpendicular to the magnetic field, which is v sin theta. What is the path followed by the charged particle in this case? So therefore it will follow a helical path. In this case, it will follow a helical path like this. It will be a helix. So option C is the correct answer. Then question number 42, a proton beam, one proton beam is there which enters a magnetic field of intensity. The magnetic field is of intensity 10 power minus 4 Weber per meter square. It enters normally. The proton beam enters a magnetic field. If the specific charge of the proton, which is charge by mass for the proton, that is 10 power 11 coulomb per kg, and its velocity, that is 10 power 9 meter per second, then the radius of the circle described will be actually here we should simply assume that the velocity is 10 power 9 meter per second, but no object can have velocity more than the speed of light, which is 3 into 10 raised to 8. So here it is simply a hypothetical case. Okay, so the radius of the circle, that is equal to r is equal to mv by qb, mv by eb. So so e by m is 10 power 11, so m by e, that will be equal to 10 power minus 11 kg per coulomb. Okay. So therefore this will be 10 power minus 11 into velocity, that is 10 power 9, divided by b, that is 10 power minus 4. So in meter it will come. So this will be 10 power 4 plus 9 minus 11, which is equal to, plus 9 is 13, so 10 power 2 meter, which is 100 meter. So option D is the correct answer. Then it is told two concentric coils, each of radius equal to 2 pi centimeter, are placed right angles to each other. Placed at right angles to each other. It means that one coil is kept like this and one coil is kept like this. So both their radiuses are same. Both their radii are same. One coil is kept like this. So both their radii are same, r and r. R is equal to 2 pi centimeter. So kept at right angles. If 3 ampere and 4 ampere are the currents through the coils, flowing through the two coils respectively, then the magnetic induction at the center of the coils will be how much? So let's suppose I tell this is x-axis, this is y-axis, this is then this will be the z-axis, which is outwards. Then 3 ampere, then it means that if we apply the right hand thumb rule, then due to the first coil, if I say I1 is current flowing through the coil 1, and so the coil 1 is in the xy plane, and the coil 2 is in the xz plane. So for the coil 1, the magnetic field, that is B1, that will come along negative x-axis, means it is along negative k cap, and plus the magnetic field due to the second coil, that will be along y-axis, since it is on the xz plane. So if we apply right hand thumb rule, it will come along the along the positive y-axis, so it is along j cap. The magnetic induction at the center, so the resultant will be at some angle with the z-axis and the y-axis. So the net magnetic field is in the yz plane. Okay. So therefore the net magnetic field at the center, that is equal to B1 minus k cap. Now B1 is so the current I2 is 4 ampere to the coil 2 and I1 is 3 ampere to the coil 1. So B1 will be mu naught I1 by 2 R1 to R, okay, which is minus k cap, and plus this will be B2, which is mu naught I2 by 2R, which is along j cap. So this we can say this is mu naught by 2R into I2 j cap, which is 4 j cap minus 3 k cap. So this is B net, the net magnetic field at the center. So mu naught by 2R, so mu naught is 4 pi into 10 power minus 7 divided by 2R. 2R will be R is 2 pi centimeter. So this is 4 pi into centimeter means 10 power minus 2 meter. So into 4 j cap minus 3 k cap. This is the net magnetic field. So we need to find the magnitude of the net magnetic field at the center only. So this is equal to 4 j cap minus 3 k cap, this much Tesla, or I can say in Weber per meter square. So this will be into 10 power minus 5 Weber per meter square. So this is B net. So we need to find the magnitude only. Therefore, the magnitude of the net magnetic field at the center, that will be equal to, so square root of 4 square plus 3 square into 10 power minus 5, which is 5 into 10 power minus 5 Weber per meter square. So option D is the correct answer. Then in question number 44, it is told two parallel wires 1 meter apart carry currents of 1 ampere and 3 ampere respectively in the opposite directions. So I1 is 1 ampere and this is 3 ampere, which is suppose I2 I tell. So the force per unit length acting between these two wires is, so we know that the parallel currents will attract and anti-parallel currents will repel. So there will be repulsion obviously in between them. So we can also prove that there will be repulsion. How? Suppose if we use the right hand palm rule, then if we say that this is the thumb of the right hand, then it is flowing along the thumb. So the magnetic field due to the first wire, the magnetic field due to the wire 1 at a point on the wire 2, that will be inwards. So if we find the magnetic force on it, if we find the magnetic force on the wire 2, due to the magnetic field caused by wire 1, that will be IL cross B. So it will be towards the right. So it will be repulsive. So now what will be the force acting? So the two wires are 1 meter apart. So now the magnetic field on the wire 2, okay, the magnetic field on the wire 2, that will, and due to the wire 1, I can say B21. B21, I'm saying it is the magnetic field on the wire 2 due to the wire 1. So that will be equal to mu naught I by 2 pi r. So that is mu naught I1 by 2 pi r, where r is this 1 meter. And therefore the magnetic force on the wire 2 due to the wire 1, that will be equal to I2, the current in the wire 2, into L2 into B21. So that will be, and here we are being asked to find force per unit length acting in between these two wires. So force on the wire 2 by the length of the wire 2, which is force per unit length, we can say. So this will be I2 into B21, which is equal to mu naught into I1 I2 by 2 pi into r. So this will be mu naught, that is 4 pi into 10 power minus 7 into I1 is 1, I2 is 3. So this will come in Newton per meter divided by 2 pi into r. R is 1 meter. The two parallel wires are 1 meter apart. So 2 pi into 2 is 4 pi. So this is 2 3 is 6. 6 into 10 power minus 7 Newton per meter, which is, and it should be repulsive. So option D is the correct answer. Okay, 6 into 10 power minus 7. Sorry. So option C. Option C is the correct answer. Good. Okay. Then in question number 45, it is told a galvanometer of resistance 50 ohm gives a full scale deflection. So the resistance of the galvanometer Rg, that is 50 ohm, and this is the galvanometer, and it gives a full scale deflection for this is 0.5 milliampere. Since why 0.5 milliampere means it is 5 into 10 power minus 4 ampere. So it gives a full scale deflection for this. The resistance that should be connected in series with the galvanometer, the resistance that should be connected in series with the galvanometer to read 3 volts is to read 3 volts. So it means that when a large resistance is connected in series with the galvanometer, then it is converted to a voltmeter. So it means that the net voltage across means the net potential difference V across this galvanometer and the resistance that is connected, that is the net voltage that should be read. So it means the voltmeter has to read 3 volts. So it means that the current that is flowing means that this Ig, the current through the galvanometer that is flowing, so Ig into the R equivalent, which is Rg plus R, that should be equal to 3 volts. So this resistance R should be how much? That is asked. So I is 0.5 milliampere, so 5 into 10 power minus 4 into Rg, which is 50, plus R, that is equal to 3. So 50 plus R, that is equal to 3 by 5 into 10 power minus 4. So which is 3 into 10 power 4 divided by 5 is equal to 30 into 10 power 3 divided by 5. So 50 plus R is 6 into 1000. So 50 plus R, that is equal to 6000. So R is equal to 5950 ohm. So it means that option B is the correct answer. It means that 5950 ohm should be connected in series with the galvanometer to read 3 volts. Then in question number 46, it is told a cyclotron is used to accelerate. A cyclotron is used to accelerate only positively charged particles, both positive and negatively charged particles. Neutron, only negatively charged particles. So option B is the correct answer. Since cyclotron is used to accelerate any charged particles. Cyclotron is used to accelerate any charged particle. But if it is uncharged, then it cannot accelerate that. So it means that neutron cannot be accelerated. So option B is the correct answer. Then in question number 47, it is told a proton is projected with a uniform velocity v along the axis of a current carrying solenoid. So there is a current carrying solenoid. It is carrying some current I. A proton is projected with a uniform velocity v. Proton along the axis. The proton will be accelerated along the axis. The proton's path will be circular along the axis. The proton moves along the helical path. So the proton will continue to move with velocity along v along x-axis. Okay. So it means that the magnetic field in case of a solenoid along the axis, that is a uniform magnetic field, which is mu naught into Ni, where N is the number of turns per unit length in the solenoid. So the magnetic field is also along the axis and the velocity is also acting along the axis. So there is no magnetic force. Since why? Magnetic force on a charged particle, magnetic force on any charged particle in the presence of an external magnetic field, that is given as qv cross b. Now if the velocity is along, if the velocity is parallel to the external magnetic field, then the net, then v cross b will become 0. So there is no net magnetic force on the proton here. So since there is no force, so it will not be accelerated. So it will continue to move with that same uniform velocity v along the axis. So option D is the correct answer. In question number 48, it is told, in the cyclotron, as radius of the circular path of the charged particle increases, in a cyclotron, as the radius of the circular path of the charged particle increases, omega equal to the angular velocity, v is the linear velocity. So the radius is given as r equal to mv by qb. So now the velocity is increased at regular intervals, then so the radius gets increased. So after every half rotation, the velocity is increased. The radius of charged particle increases. So as radius increases, then omega is actually qb by m. So this remains constant. So v increases, actually v will increase, but omega will remain constant. So it means option C is the correct answer. In question number 49, it is told, a conducting wire carrying current is arranged as shown. The magnetic field at the point O, that is how much? So now, due to these two parts, these two straight wires, there is no magnetic field at the point O. Since why? At the point O, there is no magnetic field due to these straight wires. Since why? Since this point lies on the line of these two straight wires, so there is no magnetic field due to these straight parts. Okay. So this angle is 60 degree. To these straight parts. Okay. So now, how much is the magnetic field here? So due to these circular parts only, the net magnetic field will be produced at the point O. So we know that due to a circular arc having, which is subtending an angle theta at the center, if I current is flowing, then the magnetic field due to this part, that is given as mu naught ni by 2r, where r is the radius of this arc. Now n is what? N is the number of turns. So now when the angle theta will be equal to 360 degree, then the number of turns is 1. So when the angle is theta, then the number of turns is theta by 360. So it means that here I will use theta by 360 into mu naught I by 2r. So it means here also, now due to this part, the magnetic field will be inwards if I use the right hand thumb rule, and due to this part it will be outwards. Due to this part it will be outwards. So it means that we have to subtract them. So let's say the magnetic field due to this part, that is inwards, that I call it as B1, and due to the outer circular part, that is B2, which is outwards. So the net magnetic field, that is, I can say that is B1 minus B2. So B1 is mu naught I by 2 R1 into theta by 360, that is 60 by 360. Then minus B2, that is mu naught I by 2 R2 into 60 by 360. So that is 66 360. Okay, so this will be mu naught I by 12 I can take as common into 1 by R1 minus 1 by R2 I can write. Okay, mu naught I by 12 into 1 by R1 minus 1 by R2. So option A is the correct answer. Number 49. Okay. Then in question number 50, it is told a galvanometer coil is there. A galvanometer coil which is having resistance Rg, which is 50 ohm, and the meter shows full scale deflection for a current of 5 milliampere. This galvanometer is converted to a voltmeter of range 0 to 20 volt by connecting. So when the galvanometer, when a large resistance R is connected in series with the galvanometer, then this can be converted to a voltmeter. So now the range of the voltmeter is 0 to 20 volts. So the maximum voltage that it should read, that is 20 volts. So now it means that this entire thing is the voltmeter when this R is connected in series with the galvanometer G. So this is 20 volts. This should be 20 volts across this. So if Ig is 5 milliampere, so therefore the voltage drop across the voltmeter, that is IR, Ig into Rg plus R, that is equal to 20 volts. So Ig is 5 milliampere, so 5 into 10 power minus 3 ampere into Rg is 50 plus R, that should be equal to 20. So it means 50 plus R, that should be equal to 20 by 5 into 10 power minus 3. So this is equal to 20 into 1000 by 5. So 5 4s are 20, so 4000. So R will be equal to 4000 minus 50, that should be equal to 3950. So 3950 ohm should be connected in series with the galvanometer. So option A is the correct answer. Okay. Question number 51, it is told the magnetic field at the center of a current carrying loop of radius, there is a loop of radius 0.1 meter. The magnetic field at the center is 5 root 5 times at a point on its axis. At a point on its axis. Then the distance of this point from the center of the loop is how much? Let's say the distance of this point P from the center of this loop, that is x. Now if the magnetic field at this point is B, then the magnetic field at the center, which is O, B naught, that is equal to 5 root 5 times B. Means 5 root 5 times the magnetic field at this point. So then the distance of this point from the center of the loop, means x we have to find. So let's say the radius of the loop is R. Now therefore the magnetic field at the point P, that will be given as mu naught IR square by 2 into x square plus R square whole power 3 by 2. And the magnetic field at the center B naught, that is equal to mu naught I by 2R. So therefore this should be equal to 5 root 5 times of this B. is mu naught I r square by 2 into x square plus r square whole power 3 by 2. So now here mu naught I and mu naught I will cancel out. 2 and 2 will also get cancelled. Now this is 5 root 5. Now if we take, if we cross multiply, this will be x square plus r square whole power 3 by 2, that is equal to 5 root 5 into r power 3. Now if we square both sides, then we will get x square plus r square, okay, x square plus r square whole cube, that will be equal to 5 is 25, 25 into 5 is 125, 125 r power 6. So then this will be x square whole cube, that is okay. By 2r, okay, 5 root 5. So this will be x square whole cube, that is x power 6. Now we have to take the cube root on both sides. We have to take the cube root. So this will be x square plus r square. That will be equal to 5r square. 5r square. So this will be x square will be equal to 4r square. Now if we take the square root on both sides, then x will be equal to 2r. So it means 2 into 0.1. So that is 0.2 meter. Option A is the correct answer. Then it is told a proton, a deuteron and an alpha particle are projected perpendicular to the direction of a uniform magnetic field, same kinetic energy. Okay, so here it is told one proton is there, one deuteron is there, and an alpha particle is there. They are projected perpendicular to the direction of a uniform magnetic field, and they are having same kinetic energy in the ratio of the radii of the circular paths described by them. Now suppose the magnetic field is acting inwards throughout this region, then the radius of, we have to find the ratio of radiuses of the proton and the radius of the deuteron and the radius of the alpha particle. So this we have to find. So the radius of any charged particle in a magnetic field, the radius of any charged particle in the magnetic field, that is given as mv by qb. mv by qb. So we know that the momentum of the charged particle, that is p, that is given as mv, and p square by 2m, that is equal to kinetic energy. So p, we can say that is equal to 2 into mass into kinetic energy. So this is square root of 2m into kinetic energy by QB. So it means here for all of them, the kinetic energy is same and the magnetic field is also same, but their charges and masses are not same. So therefore here the radius is proportional to root over mass by charge, root over m by q. So it means this ratio will be the ratio of, sorry, so for the proton, the mass is suppose m, and so proton means we can say that is H11, and deuteron means we can say it is H12, and alpha particle means it is He24, means it is a helium nucleus. So that is, so the proton has mass suppose m and charge is E, is 2. Mass, the square root of mass of the deuteron is 2m and the charge is E, and square root of mass of alpha particle is 4m and charge is 2e. So therefore this will be root over m by e is 2. This is root 2 into root over m by e. This also it is root 2, means it is to root 2 into root over m by e. So root m by e I can cancel out. So this is 1 is to root 2 is to root 2. So option A is the correct answer. Here, okay. Sorry, this is charge. This charge is outside the root. Sorry, this charge is outside the root. So this is root over m by q. So this will be root over mass of proton is suppose m, charge is E, mass of deuteron is 2m and charge is E, mass of alpha particle is 4m and charge is 2e. So this will be root over m by e, and this will be is to root 2 into root over m by e. Sorry, this is wrong. This is root 2 into root m by e. This is 2 into root m by 2e. So 2 and 2 will cancel. So root m by e, if I cancel out, then this is coming 1 is to root 2 is to 1. So option B is the correct answer. Then a straight wire of length, a straight wire is there, which is having length 50 centimeter, and it is carrying a current of 2.5 ampere. It is suspended in mid-air by a uniform magnetic field. It is suspended in mid-air by a uniform magnetic field. So it means that the magnetic field should be acting inwards, then only the magnetic force on it is given as IL cross B, ILB, that will be acting upwards, and that magnetic force will balance the weight of the wire. So therefore the magnetic force is given as, so that should be equal to mg. So ILB should be equal to mg. Now the mass of the wire is being asked, so mass is equal to ILB by g. So I is given as 2.5 ampere and length is 50 centimeters, so it is 0.5 meter, 0.5 meter into the field. The field is given as 0.5 Tesla. 0.5 divided by g, which is 10. So this will be like, so this much in kg it will come. So if we multiply by 1000, then in gram it can come. So the mass is 2.5 into 0.25, 5 5 is 25 by 10 into 1000, this much gram. So 10 will cancel. So 0.25 into 100 is 25. 25 into 2.5, that is equal to 62.5 gram. Mass of the wire is 62.5 gram. So option C is the correct answer. A galvanometer of resistance 50 ohm. One galvanometer is there. Its resistance Rg is 50 ohm. Galvanometer is connected to a battery. It is connected to a battery of 3 volts with a resistance of 2950 ohm in series with it. So this is connected with a battery of 3 volts. So a large resistance is connected in series with it. Therefore, this part is acting as a voltmeter. It is acting as a voltmeter. So it shows full scale deflection is connected to a battery of 3 volts along with the resistance of this in series, shows full scale deflection of 30 divisions. It shows full scale deflection of 30 divisions. The additional series resistance required to reduce the deflection to 20 divisions is. So one additional resistance we should connect, which is suppose R1. So that R1 should be how much to reduce the deflection to 20 divisions. It means now the voltage drop across the galvanometer, when this resistance R1 is not connected, that is equal to, so voltage is in the ratio of the resistances. This will be Rg by Rg plus R into V, that is 3 volts. Now this is equal to 30 divisions. So 30 into V naught, where V naught I am saying V naught is the voltage that is read per deflection. So this is the voltage read by the galvanometer, voltage read per unit deflection in the galvanometer. Therefore 30 V naught, that is equal to Rg is 50 by, this is 50 plus 2950 into 3. So this is 30 V naught, that is equal to 50 into 3 by, this will be 3000. So this is 1000. So V naught, that is equal to 50 to the 100. Okay, so 1 by 20 into 30, that is equal to 1 by 600 volts. Now it is told when R1, an additional series resistance is connected in series with this resistance also, then the deflection in the galvanometer is reduced to 20 divisions. It means now the voltage that is read by the galvanometer, that is Vg dash, that is equal to Rg by Rg plus R plus R1 into 3. So that is equal to 20 V naught. Then R1 is how much? So now therefore Rg, that is 50 into 3 by Rg plus R, that is 3000. So 3000 plus R1. So that is equal to 20 into V naught, that is 1 by 20 into 30. So 20 and 20 will cancel. So this is 150 by 3000 plus R1, that is equal to 1 by 30. So therefore we can say that 150 into 30, that is equal to 3000 plus R1. So therefore R1 plus 3000, that is equal to 15 is 45, so 4500. So therefore R1 is 1500. So 1500 ohm resistance we should connect in series to reduce the deflection in the galvanometer to 20 divisions. So option B is the correct answer. And in question number 55, it is told the correct Biot-Savart's law in vector form is. So the vector form of Biot-Savart's law. So the Biot-Savart's law tells that suppose some current is flowing through some wire, then the magnetic field at a point P due to some current element in the wire, due to some current element which is ideal vector on the wire at a point P, which is at the position vector r with respect to this current element, that is given as db vector, that is mu naught by 4 pi into ideal cross r by r cube. So it is mu naught I by 4 pi dl cross r by r cube. So option B is the correct answer. Then in question number 46 is told an electron is moving in a circle of radius. Electron is moving in a circle of radius r in a uniform magnetic field B. Suddenly the field is reduced to B by 2. The radius of the circular path now becomes how much? So now the radius of the circular path in a uniform magnetic field, that is given as mv by eb. So now it means that if the velocity and if the speed, mass and the charge are constant, so therefore we can say that r is inversely proportional to the strength of the magnetic field. So therefore when b is reduced to half, then the radius will be increased to 2 times. So it means that r will now go to 2r. So option B is the correct answer. Question number 57, it is told a charge q is accelerated through a potential difference v. There is some potential difference v and it is having some acceleration. It is then passed normally through a uniform magnetic field. So after this, it is passed in a region of uniform magnetic field B, where it moves in a circle of radius r. Where it moves in a circle, it will now move in a circle of radius r. The potential difference required to move it in a circle of radius 2r. Then what potential difference v1 is required so that the radius of the circle is 2r. So now the radius of the charge, particle in the uniform magnetic field, the radius of the charge particle in the uniform magnetic field, that is given as mv by qb. Now P is equal to mv, where P is called the momentum. P is the momentum of the charge particle. P is the momentum of the charge particle. So then we know that P square by 2m, that is equal to kinetic energy. So now P is equal to square root of 2m into kinetic energy. So this you can write square root of 2m into kinetic energy divided by charge q into b. Now the kinetic energy, here we can apply the principle of conservation of energy, where the gain in kinetic energy, that is equal to the, or simply it is called as the work energy theorem, where the gain in kinetic energy, that is equal to work done by the electric force on the charge, which is equal to q into v. Q into the means it is equal to charge into the potential difference. Charge into potential difference, that is equal to the work done on the charge by the electrostatic force. So the gain in kinetic energy, which is half mv square, that is equal to q into v. So now so the kinetic energy, that is equal to qv. So if we place it, if we substitute this kinetic energy k here, then we will have root over 2m qv divided by qb. Therefore the radius of the charged particle, that is given as root over 2m qv divided by qb. So this is root over 2mv by q into 1 by b. Okay, so now the radius is this. So now this radius is r, actually this radius is told r. Then to get the radius as 2r, then what should be the potential difference required? So therefore 2r, that we can say, that is equal to root over 2m into v1 divided by q into 1 by b. So this v1 is being asked. So therefore root over 2m v1 by q into 1 by b, that is equal to 2 into this radius, which is 2m v by q into 1 by b. So 1 by b will cancel out. So then if we square both sides, then we will get 2m v1 by q, that is equal to 4 into 2m v by q. So q and q will cancel, 2m will cancel. So v1, that is equal to 4v. So if we accelerate that charge by 4 times the potential difference, then we'll have the radius 2r. So option B is the correct answer. In question number 58, it is told a cyclotron oscillator frequency is 10 megahertz. Cyclotron frequency is 10 megahertz, and the operating magnetic field is 0.66 Tesla. 0.66 Tesla. If the radius of the D's is 60 centimeter, then the kinetic energy of the proton beam produced by the accelerator, that is how much? Kinetic energy produced by the accelerator is how much? Now kinetic energy is obviously half mv square. Now we know that omega, the angular frequency, now nu c, that is given as qb by 2 pi m. Yeah. And the radius of the D's, that is given as mv by qb. So that is v by omega, So r is equal to v by 2 pi into nu c. So v is equal to 2 pi into nu cyclotron frequency into r. So this, if we put it in the kinetic energy, so in place of v here, so this will be equal to half m into 2 pi nu c r whole square. So this will be 2 pi square m nu c whole square into r square. 2 pi square m into nu c square into r square. So the kinetic energy will be 2 into pi square. Pi square is, okay, nu c, that is this, nu c is 10 megahertz, means 10 into 10 power 6 hertz. And b is this. proton beam used by the accelerator. So this we can also write, this is half into m. So we can write m square v square by m. So this is p square, which is pi. So from here mv I can write this is qb into r. So this is q square b square r square by 2m. Kinetic energy, this is q square b square r square by 2m. That also we can say, or we can say this also. So therefore the kinetic energy that will be given as q square charge of the proton so q is 1.6 10 power minus 19 whole square q square b square is 0.66 whole square into r square. R is 0.6 meter. So this is equal to 0.6 whole square q square b square r square by 2m. Mass is mass is 10 1.667 into 10 power minus 27. Kinetic energy. This will be so we can also use mega electron. So the answer is asked in mega electron volt. So 1 mega electron volt, that is equal to 1.6 into 10 power minus 19 into 10 power 6 joule. So this is 1.6 into 10 power minus 13 joule. So 1 joule I can say that is equal to 1 joule is 1 by 10 1.6 into 10 power minus 13 mega electron volt. So that here the answer will come in joule. So therefore I can say this is 1.6 into 10 power minus 19 into 1.6 into 10 power minus 19 into 0.66 into 0.66 to 0.6 into 0.6 divided by 2 into 1.67 into 10 power minus 27 into 1.67 into 1.6 into 10 power minus 13 mega electron volt. So 1.6 will cancel, 10 power minus 13, this will be 10 power minus 6. Okay, so this will be 2 1.6 into 0.6 whole square into 0.66 whole square divided by 2 into 1.67 into this will be 10 power 27 minus 6 minus 19, this much mega electron volt. So this will be 25, so this is 10 square, this is 100 1.6 into 0.36 into 0.66 into 0.66 into 100 divided by 2 into 1.67. mega electron volt. So this will be 2 8 is 16. So this will be approximately 0.8 into 36 into 0.66 0.66 0.66 divided by 1.67 mega electron volt. So this is approximately 0.66 means it is approximately 2 by 3. 1.67 it means that is um, 5 by 3. So this is 0.8 into 36 into this is 2 by 3 into 2 by 3, so 4 by 9 into this is 1 by 5 by 3. So 3 3 is 9. 4 this is 4 by 5 is 0.8. So 0.8 whole square 0.64 into 0 into 36 mega electron volt. So this is approximately this is the answer is so slightly less than 36. 6 is 18, 6 is 36. So approximately 20. It's a 9. Okay, by 3 is there. So 3 12s 36. So into 12 this is. So 12. So approximately 7. So 12 fours are 48. So 0.64 into 12. So 12 fours are 48. 12 6 are 72, 76. 7.68. So it is approximately 7 mega electron volt. Option C is the correct answer. Then in question number 59, it is told toroid. So a toroid is somewhat like this. It is a circular shaped solenoid. It is a circular shaped solenoid. It is called as a toroid, and it is having 500 turns per meter length. So small n is 500. So 500 turns per meter. It is the number of turns per unit length in the toroid. If it carries a current I is 2 ampere, then the magnetic energy density inside the toroid is how much? The magnetic energy density, which is the magnetic energy per unit volume, the magnetic energy per unit volume. So that is equal to b square by 2 mu naught. Actually, magnetic energy density is b square by 2 mu naught. So the magnetic field along the axis of the the magnetic field inside the toroid, that is mu naught into Ni. So this will be mu naught into Ni divided by 2 mu naught. So mu naught into Ni whole square by 2 mu naught. So this will be half into mu naught n square I square. So mu naught is 10 power 4 pi. Sorry. So this is 4 pi into 10 power minus 7. So this is 2 pi into 10 power minus 7 into n square. N is 500 turns. So 500 into 500 into I square. I square is 2 into 2. So this will be 2 pi, so 2 into 3.14 into, so this will be in joule per meter cube. So into 3.14 into 10 power minus 7, this 500 into 2 is 10 power 3, so 10 power 6 this will be. So this will be 6.28 into 10 power minus 1, so this is 0.628 joule per meter cube. So option B is the correct answer. Then in question number 60 it is told that in a cyclotron a charged particle speeds up in a d, undergoes acceleration all the time, slows down within a d, and speeds up between the d's. Speeds up between the d's because of the magnetic field. Okay, so speeds up in the d, so it is not speeding up in the d, so it undergoes acceleration all the time, since always its velocity keeps on changing, and in between the d's the speed increases, the speed will increase, the speed increases between the d's, speed increases between the d's, and it is not because of the magnetic field, it is because of the oscillating electric field. It is because of the oscillating electric field which is obtained by the supplied AC voltage, by the supplied AC voltage source. So its speed increases in between the d's, but it undergoes acceleration all the time. So option B is the correct answer. Since its speed will continuously change, since it is going in a circular path, it is going in a circular path, so the speed is continuously increasing. Speed is continuous, the speed is kept same, but the velocity is continuously changing. So it is undergoing it is undergoing acceleration all the time. Okay, then in question number 61 it is told the number of turns in a if the number of turns in a galvanometer is tripled, both voltage and current sensitivity remains constant. So in case of a galvanometer, it is actually like this, some wire is wound around it and one external magnetic field is there. This is the magnetic field lines. So this is the pointer in the galvanometer. Now we know that the counter torque is provided by a spring. The counter torque is provided by a spring, which is equal to C into phi, where C is the spring constant. So C into phi, that is equal to the torque due to the magnetic field. So which is M cross B. M is equal to NIA. So NIA into B. NIAB. M cross B. So phi is equal to NAB by I. So NAB by C into, let's say the spring constant is K. So K phi. So I will tell NAB by K into I. So this NAB by K, this is called as the current sensitivity in the galvanometer. In the galvanometer, the current sensitivity is given as NAB by K. It means that if the number of turns is increased, then the current sensitivity, which is phi by I, it means the amount of deflection per unit change in the per unit increase in the current. So when the number of turns is increased, then the current sensitivity will also increase, with that phi by I will also increase. And the voltage sensitivity, so we know that V is equal to IR. So if the resistance in the galvanometer wire, that is R, then I is equal to V by R. Then if we replace this here, so phi will be equal to NAB by KR into V. Now this is the voltage sensitivity in the galvanometer. This is called as the voltage sensitivity. So now R is proportional to the length. So here R, I can say it is the number of turns into the resistance per unit turn. Suppose I can say it as R naught. R naught is resistance per unit turn in the wire. Resistance per unit turn. So if we replace this with R, then N and N will get cancelled. So then NAB by K into N R naught. So N and N will get cancelled. So voltage sensitivity is independent of the number of turns in the coil. So it means that if number of turns in the coil is increased, then also the currents, then also the voltage sensitivity will remain the same. Phi by V, which is the voltage sensitivity of the galvanometer, that will remain the same. So only the current sensitivity will increase. So by how much it will increase? The number of turns okay. So voltage sensitivity remains constant and current sensitivity increases 3 times. Yeah. So it means that option D is the correct answer. In question number 62, it is told a circular current loop is there of magnetic moment M. So a circular current loop is there. It is carrying current I. It is having magnetic moment M. Is in an arbitrary orientation in an external uniform magnetic field. So this circular current loop, it is having magnetic moment M, which is Ni into A. It is in an arbitrary orientation in an external magnetic field B. The work done to rotate the loop by 30 degree about an axis perpendicular to the plane. The work done to rotate the loop by 30 degree about an axis perpendicular to its plane. Okay. Perpendicular to its plane, we have to rotate that. So we know that work done, that is equal to the work done to rotate the loop, that is equal to increase in its magnetic potential energy. So the magnetic potential energy that is given as minus m dot b, which is equal to minus mb cos theta. So therefore the work done, that will be equal to um, um final minus initial. So that will be equal to, so let's suppose it was initially at 90 degrees. So initial, that was 0. Okay. So this will be, okay, so suppose initially, okay, it was at theta I, loop by 30 degree. Okay. About an axis. Okay. Okay. The work done to rotate the loop about an axis perpendicular to its plane. Okay. About an axis perpendicular to its plane. So if it is rotated about an axis perpendicular to its plane, then the magnetic moment vector M will not be rotated with respect to the external magnetic field. So it means that no work will be done. No work is done. So option C is the correct answer. In question number 63, it is told the magnetic field at the center O in the given figure, that is how much. So we know that if an arc of a circle if an arc of a circle we have, if suppose an arc of a circle we have, which is making an angle theta at the center, and it is carrying current I, then the magnetic field at the center B naught, that is given as mu naught Ni by 2r, where r is the radius of this arc. So now n is what? N is the number of turns in this arc. So when full circle if we take, then the number of turns is 1. Since why? It makes an angle of 360 degree at the center. This full arc makes angle 360 degree at the center, so no, so number of turns is 1. So if it makes theta angle at the center, then the number of turns in this case, that will be equal to theta by 360. So therefore thus at the center the magnetic field will be mu naught I by 2r into theta by 360. This we have to do. So now here we have to take this part, not 60 degrees, so this is 300 degrees. So this circular part where through which current is flowing, through which current is passing, the length of the loop through which current is passing, that is it makes an angle 300 degrees. So therefore the magnetic field at the center, that will be given as mu naught I by 2r into 300 degree by 360 degree, 300 by 360. So this will be 0 0 will cancel, 5 6 5 is 30, 6 6 is 36. So this will be 5 by 6 into mu naught I by 2r. This will be 5 by 12 into mu naught I by r. So option D is the correct answer. Then in question number 64 it is told the magnetic field at the origin due to a current element dl vector placed at a point with vector position r vector is. So at the position vector r, one small current element is there through which I current is flowing. This is ideal vector. Now the magnetic field then at the origin, that will be how much? What will be the magnetic field at the origin? So this will be the field at the center, that will be equal to mu naught I dl cross r. So with respect to this point, the magnetic field, it means the position vector of the point O with respect to this, that will be equal to minus r vector divided by r cube, and 4 pi is there. Okay, so dl cross minus r, now that will be equal to minus of dl cross r, minus of dl cross r. So this can be written as r cross dl also. So therefore the magnetic field at the center, that will be given as, which is dB actually, dB naught, that is equal to mu I into r vector cross dl divided by 4 pi into r cube. So option D is the correct answer. In question number 65 it is told in the given figure the magnetic field at the point O, that is given as how much? Magnetic field at the point O. So I current is flowing. This is the center O. This is radius r. Now I current is flowing. Then the magnetic field at the center at the point O, that is how much? So the magnetic field at the point O, due to this semi-infinite wear, okay, that is how much? So there is no magnetic field due to this semi-infinite wire, since why this point lies on the line which contains this wire. So therefore the net magnetic field at the center, that will be equal to the magnetic field due to this semi-infinite wire plus this circular part, which is suppose B2, and both will be inwards only, so we have to add those two. So B1 will be mu naught I by 4 pi r plus this will be mu naught ni by 2r. So this is mu naught I by 2r into, it has 3 by 4 turns, so this is 3 by 4. So this will be, so I can write mu naught I by mu naught, so this will be 3 by 4 mu naught I by r plus mu naught I by 4 pi r. So it means that option C is the correct answer. Sorry. 0, so mu naught I by 2r. I current is flowing. Mu naught I. Okay, so this will be mu naught I by, okay, this is 3 by 8, sorry, 3 by 8 mu naught I by r plus mu naught I by 4 by r. So 3 by 8, okay, so this is option A. So option A is the correct answer. And in question number 66, it is told, yes, a cylindrical wire is there of radius r, carries a uniform current I flowing through it. The variation of the magnetic field with distance r from the axis of the wire. So suppose a cylindrical infinite long wire is there, is very long wire. So at a distance r from it, what is the magnetic field on it? So if we are inside the cylindrical wire, where let's suppose the radius of the cylinder is r. So what will happen if r is less than r and less than or equal to r, and when r is greater than r? So for these two cases, what will be the magnetic field at those points that we have to find? Now it carries a uniform current I throughout its length. So we can write something called as the current density, which is J. Current density J, that is equal to current per unit area of cross section. So that is I by pi r square. And that is constant. J is constant. So therefore, here we shall apply the Ampere's circuital law, that closed integral B dot dl, that is equal to mu naught into I enclosed. Mu naught into I enclosed. So B, so therefore for r less than r, it means at a point where r is, where the distance from the axis is less than the radius of the cylinder. Small r is what? It is the distance of that point. Small r is the distance of that point from the axis of the cylinder. Distance of that point from the axis of that cylinder. And capital R is what? Capital R is the radius of the cylinder itself. So now for r less than r, we have to use the closed integral B dot dl. So I will use b into 2 pi r that is equal to mu naught into I enclosed. I enclosed will be j, which is I by pi r square, j into that area, which is pi small r square. So this pi will cancel out. So b here, that will be equal to mu naught, r and r will also cancel. R and r will also cancel. So this will be mu naught I by 2 pi r square into r. So it means that here b is proportional to r. So b here, b is proportional to r for r less than r, and for r greater than or equal to r, we will write b into 2 pi r, that is equal to mu naught I, simply mu naught I. So simply here b will be equal to mu naught I by 2 pi r. So here b is inversely proportional to r. So it means what? The magnetic field is inversely proportional to r for r greater than or equal to r. So it means that first the graph will be a straight line. So b versus r graph, if you want to draw. So for r less than r, it is a straight line, since this part b is proportional to r, and till r it is like that, and then after that it is inversely proportional. So it is curved. It's curved like this. So this part is inversely proportional to r. This is r equal to r. Okay. And this part is having maximum magnetic field at r equal to r, which is b maximum, which is equal to mu naught I by 2 pi r, which is happening at r equal to r, which is on the surface. So if the point is on the surface of the cylinder, so the correct graph is option A. Option A is the correct answer. Then in question number 67, it is told a cyclotron is used to accelerate protons, which is H11, and deuterons, which is H12, and alpha particles, which is He24. While exiting under similar conditions, the minimum kinetic energy is gained by. While exiting under similar conditions, the minimum kinetic energy is gained by. So we know that the kinetic energy, that is given as half mv square, and we know that mv by qb, that is equal to the radius. Now mv is called the momentum of the charged particle. mv is the momentum of the charged particle. So p square by 2m. So p is equal to mv actually, mass into velocity. Momentum means mass into velocity. So p square by 2m is equal to kinetic energy. So I can say p is equal to square root of 2m into kinetic energy. So this we can write okay. So p square by 2m. So this is p square by 2m. So now p is equal to, so from here p I can say that is equal to qb into r. So this we can write q square b square r square by 2m. This is the kinetic energy of the charged particle in a cyclotron. So under similar conditions means the magnetic field is the same and the radius also is the same. So under similar conditions means the magnetic field in the cyclotron is the same, and the radius of the charged particles are also same. Radius is also same. So then the minimum kinetic energy is gained by which one? So if these two are same, then it means that the kinetic energy that is proportional to q square by m. So now for that charged particle for which the ratio of q square by m is the highest, that will have the maximum kinetic energy gained, and for which the q square by m is the least, that will have the minimum kinetic energy gained. So for For a proton, the kinetic energy gained, that is proportional to p square by 2m. So for a proton, the value of q square by m, that is given as e square by m, where m is the mass of a proton. And for a deuteron, the value of q square by m, that is given as e square by 2m. Since why it is h12, so its mass is 2m and charge is e. For proton also, charge is e, mass is m, and for alpha particle, the mass is 4m and charge is 2e. So, and therefore we can say that the charge that for an alpha particle, the q square by m value, that is 2e whole square by 4m, which is also equal to e square by m. So therefore their ratio of kinetic energy, so the kinetic energy of proton is to the kinetic energy of the deuteron is to the kinetic energy of the alpha particle, that is equal to the ratio of the values of their q square by m, which is equal to e square by m is to e square by 2m is to e square by m. So that is equal to 1 is to half is to 1, which is equal to 2 is to 1 is to 2. So it means that the minimum kinetic energy gained, that will be for the deuteron. Therefore the deuteron will gain the minimum kinetic energy. It means that option A is the correct answer. Then in question number 68, which is the last question of this chapter on KCET. So here it is told two long straight parallel wires are at a distance 2d apart. Two long straight parallel wires are at a distance 2d apart. They are at a distance 2d apart. They carry steady equal currents flowing out of the plane of the paper. Okay. Flowing out of the plane of the paper. Currents, they carry steady equal currents. So their currents are also same. And they are at a distance 2d apart. The variation of magnetic field along the line xx dash. The variation of the magnetic field along the line xx dash. That is how much. How is that? So at some point in between the wires, due to this wire, the magnetic field will be upwards, and due to this it will be downwards. So this, at this point it will be 0, and at this point here, suppose here this will, at this point it will be upwards, and this, for this where it will be downwards. So this will be upwards, so this will be like this, and then at a region, at a point, if it is closer to the second wire, then the net field will be downwards. It will be like this. Then at some point here, the field will be downwards due to, no, the field, yeah, the field will be downwards due to this, and for this also it will be downwards. It will be downwards only. So this part will be downwards, and at infinity it will be 0 only, and here it will be, and at some point here it will be upwards. The net field will be upwards, so it will be like this. So it will be downwards, and here it will be upwards. Okay, so option D is the correct answer. So option D shows the correct graph. It shows the variation. So it shows actually the variation of the magnetic field with R. Okay, so option D is the correct answer. Okay, so hope all of you have understood the solutions of these all 68 questions which we have solved here. If in any step if you are unable to understand or any other kind of doubt you have, then please write that in the comments section. We shall obviously clarify them in the subsequent videos. And please install our Sapience education application, where we shall upload some very important homework questions on every chapter. So thank you everyone